In the last video, we looked at ways in which we can measure and design for reliability, which increase the chances of the system doing its job over the intended lifetime. But in real life, it's very rare for anything just to work from when the customer takes it out of the box and keeps going until its job is finished without any attention. Particularly, this is true for any expensive, complex system, which we're going to expect to last for many years.
The attention that we give a system so that they maintain their quality over their lifetime is called maintenance. But we need to start with an overarching concept of logistics. This was originally a military term for the art of moving and quartering troops. It's now moved into general terminology, and according to Chambers' 20th Century Dictionary, it has two related meanings which are shown here. Firstly, the organising of everything needed for any large-scale operation, and secondly, the control and regulation of the flow of goods and material, etc., in a business. In the systems engineering concept, logistics is the term we use for all the activity in support of the system during its operational phase, particularly from the player's point of view. It involves the distribution of consumables and spares to the system in the field, the management of support personnel, the maintenance of the system, any validation exercises, and indeed anything that is done to the system during its post-delivery lifecycle stages. The first three are primarily related to maintenance, and as they dominate, maintenance is often used as a synonym for logistics. So let's look at maintenance, what it is, and some aspects of how it influences design. As you are probably by now aware, my starting point for any new concept is to look at the definition of the word. So let's look at the view of the United States Department of Defense, who, with all those aeroplanes, warships and tanks, have a great interest in maintenance. So this is the definition of maintenance in the official United States standard on how maintenance should be incorporated into defence products. There are several points about this definition that we should note. Firstly, it mentions both retained in and restored to, from which we can conclude that there may be at least two different types of activity. Secondly, note that success is defined as maintaining a specified state, that is, meeting its objectives. It relates to sustaining the system's quality. Thirdly, using the word prescribed implies maintenance is considered as an intentional design function that is incorporated into the system intentionally. And those last two factors make it a systems engineering activity. It's not just big government customers buying F-35s and aircraft carriers that are interested in how maintenance is incorporated into a system. This concern covers almost everything that you buy. For example, mobile phones need batteries that charge. Now, charging a battery is maintenance, so you will be concerned about the charger. What mains plug does it have? What voltage does it operate at? And most importantly, what lead will you need? Come on, we've all been there. Maintenance has a special role in the system life cycle, as it is the thing that blurs the boundary of the handover from the supplier, the players, to the customer, the stakeholders. It means that the player cannot wash their hands of the system after they've got the money. And it means the stakeholders, the customers, have to undertake some technical tasks, however simple and menial. So after the delivery of the product, the manufacturer has to supply spares for it, issue warnings and recalls when faults are found, support the maintenance capability, and so on. And the customer has to undertake to do the specified servicing tasks and to maintain contact with the supplier, and so on. Consider the implications when a supplier, and think Microsoft here, withdraws support for a product that is in service. And in the civil aviation world, an aircraft cannot fly unless there is a manufacturer identified to support it, which is a role that's designated the design authority. This was a contributing factor to the withdrawal of Concorde from service. It was that Airbus, who inherited this design authority position, stated that it was unwilling to continue to undertake this role. Almost everything requires maintenance, even things that you might not at first think would. Take spacecraft. We launch them into space. Okay, if you think about it, occasionally we are able to service and maintain satellites that are put into low Earth orbit that can be reached by astronauts. But surely satellites that go out to geostationary orbit and can never be reached can't be maintained. Well, actually, there is some maintenance activity goes on. One thing is obviously frequently done is just to maintain the orbit, which could count as servicing. The other thing that's maybe a bit of a surprise is that a number of operations are done within the satellite to maintain its life and to prolong its life. Perhaps the most significant is discharging the batteries. Discharging the batteries until they're completely flat and then recharging them. This actually prolongs the battery life. And it clearly worked in this case because Inmarsat, the second flight model, lasted 23 and a half years in orbit, which is a world record. And modest cough, I was the lead mechanical engineer on that satellite. Well, in more recent times, people have begun to offer services where robotic maintenance servicing satellites can come up and essentially prolong the life of these satellites. Now, because they're not designed for more maintenance, it's not yet working terribly well, although the first one has attached itself to an Intelsat spacecraft and is prolonging its life. But maybe now this service is available, we will see communication satellites designed to be robotically serviced in orbit. There is a point about maintenance that I think is important, which is that it's not something that's just done by the customer or even something that's just done by the producer. It's where the two come together, and the producer can't just sell a product and then leave it. He has to supply some service support.
It depends how important things are, but in general, if maintenance involves actually replacing items and so forth, then the producer is probably the person who is producing the items that you do and the customer has to replace. In case of serious problems, then you may have to return the system to the producer to do it, and that introduces a problem because what you've got to do is to maintain knowledge about the system when you finish producing the system. This is something often called post-design services, and it's when it's missing can be a major problem. You have to re-engineer the system. So it's an important part of the overall keeping a knowledge base intact and expertise to handle problems.
Yeah, there's an interesting story in that I found out about operating the space shuttle, particularly in the later phases, is that the company that was operating it for NASA contracted out operating the space shuttle, discovered that quite often when they wanted a new component, the manufacturer of that component had gone out of business and NASA had not got the drawings. So they often had to take parts, reverse engineer the part, and had a manufacturing facility that was dedicated to making new parts for the shuttle that worked to the original drawings. They were just re-engineered from the bits that were lost.
Yes.
Now, I know in aircraft that's not acceptable.
No.
So any aircraft that's flying has to have a manufacturer that is supporting it. It has to be an identified manufacturer supporting
a design
it.
authority.
A design authority,
yes.
That's the word. So the words we're looking for are design authority and post-design services.
Yes. Yeah. We've already seen that from the Department of Defence definition that maintenance means actions during the operational life that are either retain or restore a system's performance. This leads to two separate activities, servicing and repair. More formally, these are called preventive maintenance and corrective maintenance. Let us start with preventive maintenance or servicing. That is, the actions that are conducted during the system's operational life as a nominal part of the system operations, and whose function is to maintain the system's quality. We can plan to do these servicing actions if we can predict the system's behaviour over its lifetime. The designers will know how quickly it will consume things like fuel or battery power, so they can predict when to refill or recharge the system before it stops working. They should also have established the things that will wear out or otherwise be unreliable with time and require checking, as they can be replaced before they actually fail. So these are the actions that the user does as part of operating the system, often without really thinking about it. Servicing functions fall into 4 different types of action. First, replace consumables, or replace parts with limited life, or adjust the system, or inspect areas of concern. Because it's a normal and intended part of the system function, preventative maintenance does not fall outside the system specification. Therefore, it's not grounds for a legal complaint against the producer when the system stops working because the servicing was not conducted. After all, you could hardly sue BMW because your Mini ran out of petrol. Preventative maintenance requirements are often explicitly be included in the requirement specification, and if not there, it should be defined in the design specification. The exception is modifications to the system to correct an identified design weakness. Car recalls are a classic consumer example. Because it's done to reduce the risk of failure rather than as a response to an actual system failure, it's called preventative maintenance. However, as it is a response to what is effectively a failure to meet the specification fully, it is legally the responsibility of the producer to put it right, and is logically a type of corrective maintenance. So let us now turn our attention to that.
Corrective maintenance, or to put it in a more succinct and using more common language, repair, are the actions that are conducted because a system has an unexpected failure to meet its specification, either because it broke down on its own accord or because it was involved in some form of incident which caused it to break. And, of course, the function of corrective maintenance is to restore the system's quality. Repair can be in one of 2 forms. You either rework the originally installed item until it works again, or you replace the originally installed broken item with a new one. A key element of corrective maintenance is the detection of failure. Some failures do not show up directly in the overall system performance until secondary and normally much more expensive failures occur. Corrective maintenance is by definition unexpected, but to a degree one can design to expect the unexpected and increase the ease of repair activities. Starting with that feature of detection we've just mentioned, that is making sure that the failure is detected. With many complex systems, it may not be immediately apparent that the system has a failure. For example, if the brakes fail in a car, the driver will only be aware of this when they try to use them. Many would consider that maybe a little too late. So the car has warning lights to tell you that you may have a brake failure, or for example you may have low oil pressure, telling you to do something about the oil before the engine seizes. Often also inspection activities like checking the oil, checking the condition of the brakes during servicing is part of this failure detection strategy. So what other design features can we employ to assist repair? Well, the first thing is protection. That is putting barriers in that prevent hazards potentially causing any failure reaching other sensitive components. We don't get chains of failures. Another important point is to design access routes that enable the components that we're likely to be needing to look at and replace to be both reachable and replaceable. So that brings in removability. We design elements that can be removed if required, such as we bolt an electronics box into the main system as opposed to welding it in. And then finally there's weak links. That is, if you can put a weak link into the chain so any failure will happen in that cheap accessible component rather than an expensive inaccessible component elsewhere in the train, then of course you would do that. And this is the philosophy behind a fuse box. One of the key concerns in designing maintenance on aircraft is to minimise the maintenance time that's needed to be spent on it. Of course, while that's happening, it can't fly. This is measured by availability, which we're going to cover a little later. But the key philosophy to speed up maintenance on aircraft is to identify the unit that is to be replaced without necessarily establishing what is precisely wrong with the unit. Then remove and replace the whole unit. The removed unit can then be worked on without affecting the aircraft operation. This was the philosophy behind the ARINC 400 ATR units, which are designed for precisely this, to speed up replacing units on aircraft to keep them flying. But generically, any unit that is designed for removal during maintenance is called a line replaceable unit, or LUR. Likewise, in space, if a unit has been designed for removal by a spacesuited astronaut, it's called an orbital replaceable unit, an ORU. With the move to integrated avionics, with avionics generally electronic shrinking so much, where the things are covered in cabinets that contain these sort of standard electronic cards, it's the cards that are replaced. And in this case, the cards are called line replaceable modules, LRMs. Another example is the 19-inch rack standard for electronic units, so that they can be located together in a way that individual units can be easily removed and replaced. It is a standard that was devised by AT&T in 1922 for telephone exchanges, but it is now used almost everywhere, including in computing and music recording equipment. And here is some sound equipment that I have that uses that 19-inch rack standard. It has even reached into space. In the non-Russian parts of the International Space Station, the modules are outfitted with standard racks which themselves are based on 2 columns of 19-inch rack-mounted equipment. Perhaps we should just consider weak links for a moment. The classic and obvious one are fuses, where you blow a fuse rather than some more expensive electronic component further down the line. Another one is bumpers on a car, so that if you have a small biff, then there's an easily replaceable body panel rather than an expensive panel that's welded into the main structure. I actually have a sort of rather a sore point with fuses. Back in the mid-1980s, I was an early adopter of laptops, this one in specifically a Toshiba 2100. I was based in New York at the time, and so was shuttling from New York to Britain a lot, and this machine had a voltage selector on the back, so I could use it in either country. But of course, being frequently jet lag, you would forget to change the voltage selector. Now, when you were in New York, it just meant the machine didn't work until you worked out that you needed to reset the voltage. However, if you do it the other way around, which I once did, of course, bang, something blows in the machine. So you phone up Toshiba and they say, well, they'll only service it on site. So a man comes in to service the machine, which meant I could see the power card as it came out the machine. And sure enough, as you'd expect, they'd used fuses to prevent the main circuitry being damaged. But only one of the fuses was in a fuse holder. The other one they had soldered into the board. So you had to replace the whole board at over £900, and that's 1980s £900. I can't help feeling that this was deliberate. It's certainly not good practice. If you're going to put a weak link into the circuit, then you make it so that the weak link is easily replaceable, or it doesn't serve any purpose. Not really very ethical, was it?
Preventive maintenance and corrective maintenance between them cover all the activities that keep a system quality during its life.
But there is another sort of maintenance that's less obvious, but in some cases can be more important. So let's look at that. The last sort of maintenance you might not even consider as maintenance, but officially it is classed as such. It is upgrading. That is, upgrading a system so it can do something new. And this formally is called adaptive maintenance. It is the actions that are conducted during the system's operational life to change the performance such that it meets a new requirement, which has the knock-on consequence of redefining what gives the system quality. It may sound initially that this is of no concern during the system design stage, but actually expandability can be specified. If customers want expansion potential, they must put the requirements for it in the requirement specification. This involves leaving capacity in the system beyond that is required to meet its immediate objectives, and then entry points to give access to this capability, which are called hooks and scars. In one paper I saw someone describe hooks as physical connection points and scars as software entry points, but I'm not sure that this is a widely used distinction. I think a better distinction, if there is any, is that hooks are the accommodation allowances generally and scars are the openings that allow connections into the system. Everyday examples are a towing hook on a car or the expansion slots on the back of a tower PC. Here is another example of designing for adaptive maintenance, and it can be seen here on my bass guitar pedal board. The elements of the system are obviously the pedals, and there's also a power supply around the back and an overall structure. And its purpose is to alter the signal that comes in here from the guitar or bass guitar and process it to make it sound the way I would like it to sound, and then feed a signal out either to an amplifier or a PA system or a recording desk or whatever. So in itself it would be considered in the overall guitar system part a subsystem of the guitar system, but in this case we're going to consider it as a system in its own right. And you can see here that it has had, well, just first thing you can see, it's had a bit of corrective maintenance to keep the tuner on the board securely. But at the moment this board is doing what I want. But you'll notice here there is a bit of Velcro strip ready, and there's a power plug, so that a further box, not this one, can be added. Now at the moment I don't know what I want it to do, if anything. I don't know whether I want it to be a phasey wazy or a flangy wangy or even a fuzzy buzzy sound, but the hooks and scars are already here, so I can add them to this board without having to start all over again. The final important concern about maintenance for the user is how much time the maintenance takes, because in almost all cases, and I may say somewhat obviously, when a system is being serviced, it cannot also be used to perform its function. So we need an objective definition of maintenance time so that it can be incorporated into the requirements in a measurable way. This can be a very serious concern. Filling a car with petrol takes 5 minutes and can be easily fitted into most domestic car usage. But charging an electric car takes hours, which may prove more difficult to plan for. So the car may not always be able to do the journeys that we would like it to do. And that may be a serious concern deciding the decision to purchase it or not. This time taken by maintenance is called the maintenance downtime, and it has 3 components. The first component is the waiting or the administration time. This is the time from the detection of the need for maintenance to the start of active maintenance happening, excluding any logistics time. And that brings us to the second component of maintenance downtime, which is the logistics or supply time. This is the time for the items required for maintenance, that is the parts, the tooling and even the facilities, to become available for use. The third component of maintenance downtime is the actual maintenance time. That is the actual time it takes for the maintenance activity to be conducted on the system. Now, in theory, administration time and logistics time should really only apply to corrective maintenance, since the system can be operational while preparation for preventative maintenance is being performed and therefore the system is not out of action. However, any car owner will know the practice in real life. So there we have it. Obviously, maintenance can greatly affect the customer's experience of using a system. And that is something that you would really want to nail in the requirement specification. The question is, how? One way to do this is the concept of availability. Availability is a measure of how much of the overall operational life of the system is it actually operational, either in use or ready for use. I want to use the system. What is the probability I can? In other words, it is a measure of the time lost to maintenance activities compared to the total system lifetime. It's measured as a probability, and so an availability of 50% would mean that for half the time of the system it is in for maintenance and cannot be used. Aircraft with low availability are often called hangar queens, and in the 1980s some fighter aircraft could only achieve availabilities of 14%. Availability can be defined in three ways. The first type of availability is inherent availability. As the name suggests, this is the underlying probability that the system will be available with quality due to its design and build, and it corresponds most closely to reliability. It is the factor of total time spent on planned preventative maintenance, and it ignores any time lost due to corrective maintenance, and it is something that is in the control of the system builders and could be placed in a system requirement specification. The next type is achieved availability, and this differs from inherent availability in that it includes the corrective as well as the preventative maintenance. Now, the designer cannot control the amount of corrective maintenance, as that is due to how the operator uses it. However, it is the availability that best defines how good the system design is. Because although achieved availability could not be directly specified, there could be requirements on how long and expensive likely repairs will take. Finally, there is operational availability, and this is the measure of how often the system is actually ready in the real world when required to do so. So in addition to the time required to perform the various types of maintenance, it includes all those real life effects that are covered in maintenance downtime. This is difficult to establish at the design stage, as the maintenance downtime is more the responsibility of the operator, and so is a metric more often used to evaluate them. Let's put this in aircraft terms. Inherent availability is in the hands of the aircraft constructor, the Boeing, the Airbus, and they can determine how much preventative maintenance their aircraft requires. Now, the achieved availability is a grey area between the constructor, the Airbuses and the Boeings, and the airliners, the British Airways and the Qantases and the Emirates of this world. The constructor does have this control about how long and difficult it is to perform a repair. But it is the airline, the British Airways, etc., who control how often that repair is needed. And then we come to operational availability, and this is pretty much in the control of the airline. How well are they managing their logistics?
Well, Mark, I think it's time for this video's summary.
Yep, and here it is. We started with a concept of logistics, which is just a term we use to define everything that we do to a system when it's in its operational life. And we saw that the biggest and most important part of that is maintenance, which are all the activities that are required to maintain the system's quality in service. We saw that there are three types of maintenance. The first type is preventative maintenance, which we would normally call servicing. The second type type is corrective maintenance, which we would normally call repair, and the third type is adaptive maintenance, which we would normally call upgrade. Now, maintenance takes time, and while a system is being worked on, that is a loss of operating time, and we can measure that in a concept of availability, which is the probability that the system is there with its quality when it is wanted. And again, there are three types. There is inherent availability that measures the loss due to planned preventative maintenance, achieved availability that measures the time lost to both preventative maintenance and corrective maintenance, and then there is operational availability that measures all the real world time lost due to the maintenance downtime that includes all the administration and logistics time.
In the next video, we'll look at the third area that the Quality Control Department normally covers, and that is safety.